Okay, we're on problem 6. This is still section 10.1, by the way. It says, in the plane figure illustrated here, only movement that tends downward is allowed. Okay, list the number of paths from A to B. Right, your answer is a set. Okay, so let's see. What if I go A to C? Now from C I can go to E, and then I have to go to H and then down to B. Or I can go from C and then over to F, and then I got these three options down to B. Okay, so what if I go A to C? E, H, B, that's going to be 1. A, C, F, H, B, that'd be 2. A, C, F, B, that'd be 3. A, C, F, I, B, that'd be 4. Okay? That's going to be everything from A to C. What if I go A to F? Okay, from F I got these three options, then down to B. So I can go A to F to H to B, A to F down to B, A to F to I to B. Okay, and I think that's going to be it for A to F. Okay, now what if I go A to D? From D I can go over to G, and then down to I, and then down to B, and then or I can go A to D, over to F, and then take one of these three options down to B. Okay, so let me consider that A, D, G, I, B, that'd be that one. A, D, F. From F I can go to H and then down to B. Or I can go A, D, F down to B. Okay, that'd be that one. A, D, F, I to B. Okay, that'd be that one. So if I count the number of paths that I just took, there'd be 11 paths from A to B. Okay. Problem 7. How many integers between 100 and 400 contain the digit 2 as one of these three digits? Okay, so the thing to do here is, it'd be way too difficult to think, okay, I got 203, I got, 382, So, okay, so the plan here is, what if we have a digit of 2 leading off? And then what if we have a digit of 2 in the second space? And what if we have a digit of 2 in the last space? Okay, now we don't want to overcount anything. So what if I have a digit of 2 in the first space? Well, that means I'm going to have a number in the 200s. Okay, 200 to 299 would be 100 digits total. Okay, now I don't want to count anything else in the 200s because I've already looked at those numbers. Okay, so let's only look at numbers that are in the 100 to 199 range, or the 300 to 399 range. Of course, 100 and 400 don't contain the digit 2. So if we have a digit of 2 in the second spot, well, that means that I'm looking at a number either in the 120s or in the 320s. Okay, 120 to 129, that'd be 10 digits total. 320 to 329, that'd be 10 digits total. Okay, the other ones I just listed here. So if I have a 2 in the last spot, again, I'm only looking at numbers that are in the 100s or the 300s. So 102, 112, 122, I don't want to count that because I've already looked at 122. Okay, so 132, 142, 152, 162, 172, 182, and 92. That'd be 9 numbers total that have a 2 at the end. Okay, and then do the same thing with the 300s. So 302, 312, I don't want to look at 322 because I've already looked at that. Okay, so go to the next one, 332, 342, 352, 362, 372, 382, 392, there'd be 9 numbers total. Okay, so if I add up these numbers here, 100 plus 10 plus 10 plus 9 plus 9, that'd be 138 numbers total between 100 and 400 contain the digit 2 as one of the 3 digits. Okay. For homework in section 10.1, I'd like you to look at the problems on page 557, these listed here. And so we're going to begin section 10.2 10.2 and 10.3 are kind of related there. So let me go ahead and combine 10.2 and 10.3 in the rest of this. So a definition, it says the fundamental counting principle says that if a process consists of m steps and step number I can be done in n sub I ways, then the total process can be done in n sub 1 times n sub 2 times n sub 3 times all the way up to n sub m ways. Okay, so what you're going to do is you're going to take a look at step number I in the process. You'll figure out how many ways step I can be done. Okay, you'll do that for all the steps, and then you'll multiply all the numbers together to get the number of ways that the total process could be done. I've got some examples here where we're going to be using the fundamental accounting principle. So problem 8, a customer orders a hamburger with or without the following ingredients: lettuce, tomatoes, onions, ketchup, mustard, or cheese. Okay, how many ways can a hamburger be ordered? Okay, well, basically you're going to go through each ingredient. I'll lay out 6 spaces here, and it'd be yes or no to lettuce, yes or no to tomatoes, yes or no to onions, yes or no to ketchup, yes or no to mustard, yes or no to cheese. Okay, so because I'm only going to say yes or no, that's only 2 choices, and so I'm going to have 2's across the board there. Okay, 2 multiplied by itself 6 times would be 2 to the 6th power, and 2 to the 6th power is the same as 64. Okay, so there's 64 different ways that a customer can order a hamburger. That includes a hamburger with only tomato, mustard, and cheese. That includes a hamburger with everything on it. You know, if I would have said yes to all 6 of these. That includes a plain hamburger. You know, one, like if I would have said no to all 6 of these. Okay, 64 different ways. Okay, problem 9. A test has 6 multiple choice questions. Okay, part A. In how many ways can a student respond to the questions if each question has 4 possible answers? Okay, so problem 1 has 4 answers, problem 2 has 4 answers, problem 3 has 4 answers, etc. Well, basically what you're going to do is you're going to take a look at the problem, and because there's 4 choices there, you're going to have 4 times itself 6 times. Okay, so 4 times 4 times 4 times 4 times 4 times 4. Or that'd be the same as 4 to the 6th power, which 4 to the 6th power would be the same as 4,096 ways. Okay, now if I'm just guessing, I mean, even though this is a multiple choice test, 6 questions, that's not a whole lot. There's 4,096 different versions of the test, and of course only one of those is going to be the one where all 6 of them are correct. Okay, so just guessing, if you don't really know the subject matter, is not a good strategy. Part B, in how many ways can a student respond to the questions if each question has 5 possible answers? Okay, so well, similar thing. So A, B, C, D, or E. Okay, so I got 5 times 5 times 5 times 5 times 5 times 5. Okay, that'd be 5 to the 6th power. So 5 to the 6th power, if you were to check that, would be 15,625. Okay, there's that's many different versions of the test there can be. Now, again, even though it's multiple choice, there's only 6 questions, and it's not a whole lot. If a student really doesn't know what's going on, that's going to be a big problem with just random guessing there. Okay. Problem 10 says that a paint manufacturer wishes to manufacture several different paints. The categories include color, which are red, blue, white, black, green, brown, and yellow, or the type of paint, which are latex or oil, the texture paint, which is flat, semi-gloss, and high gloss, and the use of paint, whether it's indoor or outdoor paint. How many different kinds of paints can be made if you have to select one color, one type, one texture, and one use? Okay, so for this one I'm going to use the fundamental counting principle. And so I got to select a color, a type, a texture, and a use. Okay, there's should be 7 colors so I got to select one color. there should be two types, latex or oil, so select one of those. A texture, select one of those, flat, semi-gloss, or high gloss, and then two kinds of uses, whether it's indoor paint or outdoor paint, select one. Okay, so if I multiply these four numbers together, I should get 84 kinds of paint that this paint manufacturer can make. Okay, so again, all we're doing with the fundamental counting principle is we're going to take a look at step number I in the process, figure out how many ways you can do step I, and then you're going to multiply all the numbers together to get the number of ways that the total process can be done. Okay? If I look at problem, if I read this definition here, if n, which is greater than 0, is an integer, the factorial symbol, which is n factorial, is how we read that, is defined as n factorial equals 1 times 2 times 3 times etc. all the way up to n. Also, 0 factorial is defined to be 1, not 0. Okay, so problem 11, and how many ways can 6 students be lined up? Okay, well, I'm going to lay out 6 spaces there, representing the ways that 6 students can be lined up. I got 6 possibilities for the first spot. Okay, so any one of the 6 students can go on the first spot. Now, once a student has been positioned, that you got 5 left. Okay, so position 1 of the 5, position 1 of the 4, position 1 of the 3, position 1 of the 2, position 1, the last one. Okay, but 6 times 5 times 4 times 3 times 2 times 1, that would be exactly the same as 6 factorial, which is 720. Okay, and if I just show you here on the 84 version, so 6, if I hit math and then go over to PRB, here's the factorial sign. Okay, so 6 factorial gives me 720. Okay, 3 factorial, that's the same as 3 times 2 times 1, okay, or 6. 4 factorial is the same as 4 times 3 times 2 times 1, or 24. 5 factorial, that'd be the same as 5 times 4 factorial. So 5 times 24 would be 120, if you were to check that. Okay, here's 6 factorial. Okay. Problem 12, an MP3 player randomly plays 10 songs on a playlist. Part A, in how many ways can 10 songs be played if a song cannot be repeated? Okay, so once you've heard a song, you're not going to hear that same song again. You've already heard it. So now there's 10 songs on the playlist. Okay, so once you've heard a song, then there's going to be 9 songs that remain. Once you've heard one of the 9, then there's going to be 8 songs that remain. Once you've heard one of the 8, then there's going to be 7 songs that remain, etc. Okay, well, that'd be exactly 10 factorial. And 10 factorial, using your calculator, would be, if I just try it here, so 10, math, and 4, I'm getting 3,628,800 different ways that I can play these 10 songs. Okay, so quite a bit there. Part B, in how many ways can the 10 songs be played if repetition is allowed? Okay, so here's the thing. If you hear a song, it might be the case that later down the road you might hear that same song again. Okay, so I got 10 songs to play. I'll play the first one. And since repetition is allowed, all 10 songs can be played second. All 10 can be played third. All 10 can be played fourth. Okay. Of course, I'm only playing one of the songs, okay, but the fact is that repetition can be allowed there. So that's going to be 10s across the board, 10 times. 10 to the 10th power would be the same as a 1 with 10 zeros, or 10 billion. By the way, if I try to type in 10 to the 10th power. And this calculator gives me something in scientific notation. That's because 10 billion is way too large. Okay, a lot of calculators are going to leave the result as you know. So I guess if your calculator gives you a result in scientific notation, you know, go ahead and leave it as 10 to the 10th or whatever before you went to the calculator. Okay. Yeah, when we go ahead and stop right there in the notes, and in the next video I'll talk about permutations and combinations.